Good afternoon, good morning, everyone. Welcome to our webinar, Unlocking Standardless X-ray Fluorescence Analysis with Thermo Fisher Scientific UniQuant Software. I hope the audience can hear me. Is that everything? Is the audio, video, everything fine? Do you hear me? Well?
Yes, I think everything is fine.
Okay, excellent. So today, it is really our pleasure to co-host this webinar together with FLUXANA, the leading company in this XRF application area. So before we start, we'd like to introduce ourselves so that you know who we are. I will start with myself. So my name is Lynn Schneider. I'm the product manager for XRF at Thermo Fisher. I studied chemistry in Max Planck Institute in Germany and have collected extensive experience across different industries and continents. After I returned to Germany from the US, I transitioned to the scientific instrument manufacturing industry, serving as the product manager for quite some years since 2016, so almost 10 years. So today I'm going to present to you, together with my colleague Didier and Rainer, the UniQuant webinar. Now I hand it over to Didier Bonwan, my co-presenter from Thermo Fisher side. Didier.
Yes, hello, good morning, good afternoon to everyone. So my name is Didier Bonvin. I'm graduated in material science. And soon after, I started working in X-ray fluorescence. And later as a product manager, both for wavelength dispersive X-ray fluorescence and for energy dispersive X-ray fluorescence. And since now 5 years, I'm concentrating on the applications as a product application manager for the XRF portfolio of spectrometer here at Thermo Fisher Scientific. Rainer?
Thank you.
Up to you.
Yeah.
Let's go to Rainer.
Yeah, thank you very much. My name is Rainer Schramm. I also welcome everybody to our webinar today, showing UniQuant applications. And I myself, I'm the CEO of FLUXANA here in Germany. I did my studies in chemistry at the University of Duisburg, also here in Germany. And from the beginning of my academic career, I studied X-ray fluorescence analysis. So since more than 30 years, I'm working with this technique. And 2002, I founded FLUXANA as a company. And our idea is to support chemists and users worldwide using X-ray fluorescence analysis. Thank you so far.
Thank you, Rainer. Okay, now let me show you what we have prepared you today. So this is the agenda. I will start with the general introduction of UniQuant software as product, as well as the basic principle of the software. And then I will hand it over to Didier, who will give you some application examples using UniQuant software on how to fine-tune the parameters to improve the accuracy. And we will give it over to Rainer from FLUXANA. He will give you a short introduction of the company FLUXANA and some introduction of different sample preparation methods. And last but very important, he will bring you some very interesting application examples using UniQuant software and some tips how to improve the accuracy by fine-tuning some of the parameters with standards. Now, first, let me show you our XRF portfolio. We have 4 products in the ARI XRF spectrometer portfolio. The ARI Quantix ED-XRF spectrometer is the benchtop ED-XRF. The ARI Optimix XRF spectrometer is the floor standing low power WD-XRF. The Performix ARI Performix XRF is the floor standing high power sequential WD-XRF, and the ARI X900 spectrometer is the newest product in our portfolio, the successor of 9900, and it is the sequential and simultaneous WD-XRF, and you can also include the XRD in the system. And UniQuant software is available for all 4 products. Okay, before going to the software part, let me introduce you our two gearless goniometers for the standardless analysis. These are the very important element to ensure precise, accurate analysis with the UniQuant software. They offer flexible, versatile elemental analysis for routine and non-routine samples. The universal goniometer is available for the ARI Performix and X900 spectrometers, and the Smart Gonio is available for ARI Optimix and X900 spectrometers. Both goniometers are gearless. That means they have the friction-free positioning system without gears, and they have very fast continuous scanning capability. And that is very important for UniQuant because we have this feature peak-to-peak algorithm, which requires very precise and fast switching from one position to the next. With both goniometers, we have access up to 84 elements of the periodic table, and as mentioned, both can be connected with the standardless analysis. Another important feature to mention is with the FPC detector, specially designed, that it has a very low consumption of piton gas. So for approximately 2.5 years, you only need 150-liter piton gas bottle. Now, we know that XRF is a relative technology, and that means you always need to set up some standards and set up a calibration curve, and then you can measure samples and then calculate the concentration based on the intensity and the calibration curves. However, sometimes there are also situations where no standards are available. For example, you have new compounds, one-off samples, or some complex materials. That is when you need UniQuant software, which uses the fundamental parameters algorithm. With the UniQuant software advanced standardless analysis, you can obtain reliable elemental composition results within minutes for any kinds of sample. That means you can do on multi-element solids like alternative fuels, pressed powders, small samples, or air filters. The UniQuant software comes fully pre-calibrated in the factory and is ready to use standards for setting up, so everyone can get high quality results from day one. So you don't really need a standard, but of course we have some examples showing you if you add a few standards or some samples from your own with known concentration, this will further improve the accuracy of this software. Okay, how does the UniQuant software work? It is a physics-based fundamental method. The XRF technology has been really well understood in decades. So in principle, if you know all the parameters, you can calculate the intensity of the signal. For example, you know the physics, where the elemental line positions are. If you know your samples, like the compositions and metric effect, and you know the instrument, geometry of the optical path, detector, background overlaps. If all these parameters are known, you can use these parameters to apply to this very complicated equation. I don't want to overload you, but luckily we have the software that does the job for us. So UniQuant does this iterative physics-based calculation. It predicts first the potential intensity and compare with the measured intensity. And if there is a match, perfect, you get the elemental results. Otherwise, it adjusts the parameters and compare again. So it does several iterations until it has the best match. Then in that case, you get an accurate quantification without empirical standards. I mentioned the peak-to-peak algorithm that is designed for efficiency and accuracy. Let's have a look what is peak-to-peak. So instead of this conventional scanning methods, we don't scan the whole periodic table. Instead, we scan from we pick one position from one position to the next position. So it hops of one position, 1 to 2 to 3 to 4. And in this case, we measure only 122 positions instead of thousands of positions. Imagine you have a fixed measurement time. Of course, the fewer positions you need to measure, the longer the residual time on each position or the counting time on each peak you have. which means it will improve the limit detection. Also, with this hopping mechanism, you can do individual setup of counting times to focus on interesting elements. I have one example for you later. Another feature this algorithm offers is the spinning, because it is staying on one position long enough that you can spin the sample for irregular samples or smaller samples. In a word, peak-to-peak is an advantage and unique feature for UniQuant. Now let's have a look, do some math to understand how does the longer counting time improve the limit of detection. I'm sure you all know this equation, how the limit of detection is calculated. It's a very simple calculation. So 3 times the square root of the spectrum equivalent concentration divided by Q times T. T is the time of analysis in seconds. That's the counting time I've been mentioning. So let's compare the scan-based and UniQuant method. If we assume that for a scan-based method, we measure 5,000 positions, in that case, you can say approximately counting time per position is 0.1 second. Whereas for UniQuant with 120 positions for the same time, we can achieve 1 second to 20 seconds, or actually we can even achieve over 20 seconds. We have an example. And if we calculate the limit of detection of chromium in steel sample, and we know the Q and B, then we can calculate the scan-based method. You have a limited detection of 54 ppm, whereas with UniQuant, we achieve better than 17 ppm. We can even go down to almost 4 ppm. So we can really proudly say that with UniQuant, we can improve the limit of detection up to 17 times. So how does the counting time influence the accuracy? This is one practical example. This is the polymer sample, and here are the certified values of different elements. We started with sodium at the counting time 12 seconds, and we were not able to detect sodium. Then we increased the counting time to 40 seconds for sodium, but only for sodium because we don't want to extend the measurement time. And now the measured value of sodium matches really very well with the certified value. So in this example, we have a factor of 1.8 improvement at 40 seconds counting time versus at 12 second counting time. And sodium was not detectable with 12-second counting time. That means it's not possible with scan-based method if you only have this short counting time. So why did I mention spinning? Why is this spinning important? It is because when you want to analyze small or odd-shaped samples, it permits the goniometer to see more of the sample, and it allows to average out any inhomogeneities of the sample. And this is also quite important for metal samples. If you do the sample preparation through milling, and you have a lot of grooves, and this allows you to average out the grinding grooves in metals. And why can't the scan-based method use spinning of sample in the analysis position? Remember that we mentioned that the counting time is probably only 0.1 second or even less, while the spinning allows 1 revolution per second at the best. In this case, if you have this 0.1 second of sample, it's only spin for 36 degrees, so you are not seeing the whole sample. In this case, without the full revolution of the sample during analysis, the advantages of spinning of the sample are lost. So you're not really benefiting from spinning method. Okay, now I will hand it over to Didier, and he will tell you more about how to fine-tune UniQuant software parameters for accurate quantification without empirical standards. Didier, over to you.
Yes, so here are some steps to improve the accuracy with the kappa lists. The kappa list is the complete list of intensities or intrinsic sensitivity of the spectrometer. To get these kappa list, we run 64 specimen samples that are either pure compounds or pure metal sheets. They help to determine the instrument response for 100% of one given element. The kappas are expressed as counts per second per 0.1 milligram, and then they can be also fine-tuned by running a specific standard corresponding to the routine sample or the unknown sample that you want to analyze. It is not mandatory, but of course, if you want to achieve the highest accuracy, this is a way to do it. The kappa list includes both the intrinsic sensitivity for a given element, so the wanted signal. This is the kappa II, and the kappa ij. These are the overlaps, the overlaps coefficients. When two analytical lines are close together, they interfere on each other, and there is a certain unwanted signal that is read by the spectrometer that needs to be corrected for. And both with the sensitivity kappa list and with the line overlap kappa list, we can achieve then these correction for overlap elements. Then when we want to achieve the highest accuracy, here is an example for precious metal application. We can run some actual standards. In the first example on top here, it's a gold alloy. The second example is a palladium alloy, and these can be also used for dental alloys, for example, which are rather complex. And you can see that with fine-tuning, we can really reach a very good accuracy of analysis, both on gold alloys for measuring silver and copper, on the palladium alloy for measuring gold, ruthenium, copper, gallium, and zinc. Next slide. Fine-tuning will also help in the case of analysis of low alloy steel, for example. As mentioned by Ling, the rotation of the sample, so the spinning of sample during analysis is very important when analyzing alloys, metal alloys, because we find grinding grooves on the surface of the alloy, and the response for XRF is not the same if we measure the grinding rooms, if we look at the grinding rooms at 90 degrees or at 180 degrees. So it's important to have spinning of the sample during analysis, and that can be done with UniQuant. In this example here, you can see that we managed to improve quite a lot, a few elements, arsenic, cobalt, chrome, and phosphorus and sulfur, in order to achieve a better accuracy of analysis for these particular elements. And that was by adjusting or fine-tuning the kappa list. Next slide. Same can be done also for pressed pellets. Pressed pellets will be, first of all, mineral samples that are ground to fine grain size and then are pressed to obtain a nice flat surface that is presented to the spectrometer and that can be placed in the vacuum of the spectrometer. Here again, in the case of cement, there is a well-known difference, especially on sulfur. It requires a fine-tuning for the sulfate concentration in cement, but fine-tuning helps also to improve the accuracy on alumina and here on phosphorus oxide and on silica. Next slide. We need also good overlap corrections because there are some elements that will interfere very strongly on others. In this example, we have a cobalt alloy that includes a quite high concentration of tungsten as well. So you can see here we are at nearly 58% of, or so around 60% cobalt and around 8%, 9% of tungsten. And cobalt will interfere strongly on erbium. And you can see that if we do not correct properly for the overlap of cobalt on erbium, we're going to get a false positive here, quite high false positive for erbium. That is only due to the very strong presence of a very big cobalt peak due to the concentration in this sample. Then for ytterbium, that is overlapped by nickel and cerium, the false positive is much less wrong, I would say. But as you can see on the fourth column here, with the proper overlap correction, we can remove totally these false positive from the result. Next slide. And here is an example. Okay, here are two examples. On the left, it's analysis of small spots on a sand sample. A sand sample that presented some shiny little grains on the surface. And the operators were very excited because they were saying, oh, it looks like gold. So we decided, okay, let's quickly do some spot analysis. With our performing spectrometer, we can point at a 0.5 millimeter surface on the sample. And with the camera, we can select which spot we want to measure. And then we start a UniQuant analysis. And with the UniQuant analysis, of course, we are covering 122 lines that correspond to 75 different elements of the periodic table. And it's very easy then to find out what these shiny little spots are made of. And here it was pyrite, FeS2, that is well known as being shiny. And these were not at all gold flakes in the sample. On the right, it's an example for a mapping. A mapping on a manganese rock in this example, but it's also useful for other geological samples. We can select the surface to map. The mapping will be obtained by measuring several 0.5 millimeter diameter spots on the given surface. We select the surface to map either as a square or a circle or an oval or a rectangle. And then, so through the onboard camera. And then generally, we will start with a UniQuant analysis for the whole sample in order to detect the majors and the minor elements. And then when we analyze the 0.5 spots, we're going to concentrate only on the majors and minors that are of interest. This is because by moving from 0.5 millimeter spots to from 29 millimeter diameter analysis to 0.5 millimeter spots, we are decreasing the area, the analyzed area, by 3,400 times. So the signal is also decreasing by more than 3,000 times. So it becomes very difficult to detect the trace elements. But in any case, in general, we are interested mostly by the majors and minors on such a surface of a geological sample. And so by measuring the different spots, we'll be able to detect, as you can see on the right, to get a 3D mapping view of the presence, the spatial presence of the different elements, which can then inform the geologist of what the types of compounds that are found at different positions on the surface of the sample. Yeah, next slide. We can also, when we run a series of samples or collections of samples, use a function that is a template feature. We're going to enter the general data for the sample. This is very important to enter the general data to tell what is the chemistry. Do we have oxides? Do we have elements? To tell is there a dilution? Is there a rest in the sample? And then we can apply the same information for all the collection of the similar samples. And we can see that on the next slide. On next slide, you can where we measured milk-based powder samples. And here we compare the UniQuant results with ICP results. And you can see we have a quite good agreement for sodium, magnesium, potassium, calcium, and iron. So good agreement between ICP and UniQuant using an ARL Quantix spectrometer, benchtop EDXRF. Next slide. Another example now for heavier elements, rhodium, palladium, platinum. I'm losing my voice, sorry for that. And again, here we have the comparison between ICP on the vertical axis and the ARL Quantix UniQuant results. And you can see that we get quite good agreements between the two techniques. So it shows that UniQuant analysis, in this case, using a rhodium anode tube, but we can, with a primary beam filter, measure rhodium down to 2 ppm levels in terms of limit of detection, and also palladium and platinum. So that's it for my presentation. And now over to Rainer Schramm for the next continuation of this webinar.
Yeah, thank you very much, Didier. Thank you very much, Ling, to the presentation so far. I will now present you the use of UniQuant in our laboratory, just in the daily work, and give you there some practical examples. But let me start first with introducing FLUXANA shortly. So we are located at two places in Germany. There's the main headquarters in Bedburg, and here we have the production of our sample preparation machines. And we have also the main laboratory and the administration. In East Germany, in Ilmenau, we have the production of our drift monitors, which you will find in a lot of XRF instruments. We are in action since 2002, and nowadays around 60 people serving our customers. The whole business is split in 5 parts. So first of all, we do sample preparation machines like presses and fusion machines or weighing automats. We produce certified reference material with ISO 17034 accreditation. We also produce a lot of different consumables we need to do XRF analysis. The drift monitors I mentioned already, and last but not least, we have our laboratory, which is working under ISO accreditation as well, and there we do a routine analysis, but also application development. But now let us go to UniQuant, and the first example I want to present you is a class. It is a drift monitor class we produce ourselves and which is used to control a lot of application. And this class has nearly all elements from the periodic table, so this is why it's also interesting for such a software like UniQuant. And when I want to measure such a class, I have to give some information to the UniQuant. Here on the left side, you see the mask of the software where we have to enter all the data. And when we have a class, we can consider that the elements are all present as oxides. So the non-measurable elements I would have in such a class is beside the oxygen, also boron. And in this case, because I can't measure boron on this XRF machine, I would define this as a given concentration because I know there's 8.8% boron in that sample. And then UniQuant can calculate the rest of the elements. I define the sample height that is entered here. I define which copper list is used, and in this case we use the any sample, which was factory calibrated. We measure it under vacuum. We say for the background, the system, the software should select it automatically. That means normally there are 4 or 5 backgrounds already adjusted in the software, and the software automatically makes a fit which background is the best for this sample. Then we do not normalize to 100%. That means we really want every intensity converted to concentration to see then the sum of the analysis. And that is what we see here. And so quality-wise, for me, always interesting is what is the sum coming out here. And you see that this any sample-less, kappa-less fits very well to this kind of sample. And this is why then the sum fits very well to the theory. And you see that here in this sample, we find everything from fluorine starting over the light elements, then the 3D elements. Then we have here also rare earths, and it goes down until lead and bismuth. So it's really a good spread over the periodic table, and of course also a good test for such a software package. Let's present me another example. We do, of course, also a lot of fusions in our laboratory, so we have new methods to develop. And then it's, of course, also good when you have a new recipe to make first tests using such a standardless software. So what do we do normally? We take a sample. Let us think about a cement, which is calcined first. We mix it with a lithium borate. Ratio would be 1:8. And then we put it into the fusion machine, which then is heated up, let me say, to 1200 degrees. Then we agitate it when it's liquid. And when the melt is homogeneous, we pour it into a mold so that we get a glass. And then we cool it down that we can really handle it and put it in the XRF machine. When we want to measure this with UniQuant, I have to define, of course, how I want to calculate the elements. Again, we have a glass, so we know the elements are presented as oxides. And oxygen would be the only element here we cannot measure. So all the rest is measured by UniQuant. We have no additional concentration information we have to enter. Our glass bead is 3 millimeter height. We use now a kappa-less, which was optimized with a few glass beads just to fine-tune that. We measure it under vacuum. And here we use a shape, a background, which was also established by a blank glass bead. And this was really the recipe. So we diluted our sample 1/8 with a flux, which is a mixture between tetraborate and metaborate, 66% and 34%. And you see that here is the dilution factor. Here we select the flux, which is also in a library in UniQuant. And all the other parameters like the shape is defined here and so on. So and we do not normalize because we really want to see if our recipe works well. So that means if, for example, the dilution was not correct, if it's not homogeneous, we will have a deviation of 100%. And if we look on the first results, we see that here everything worked perfectly. This cement comes out like it should come out. So we have a sum very close to 100%, and everything worked very well. But now I want to show you a little bit what can happen if you tell UniQuant different information. And the first what could be changed is the flux. So that means perhaps you're not sure, you get a glass bead, you don't know what flux was used. This is very important because I just made a trial to change from my mixture to pure tetraborate. And you see for the main component, it has an influence. Also the sum goes up. That means it is really obligatory that you have to define the correct flux. Otherwise, a standardless software cannot calculate the results. Another idea is, do we really need to specify the oxygen? Sometimes we are not sure if every element is present in the highest oxidation state. So in this case, I just calculated these oxides into elements. So these are exactly the same values, just stoichiometrically calculated. And if I sum up all the oxygen which is bounded to the elements, it will be 36.4%. So these are the same figures. But now what happens if I tell UniQuant, please evaluate it as element, and I just don't tell UniQuant that there is oxygen inside, you will see you make a very big error Yeah, so this would not work because then UniQuant will just estimate there's a gap to 100% of 30%, but this is not correct because UniQuant doesn't know what is the gap, yeah, what element. So this you have to specify. If you would specify it correctly, that you say this rest is oxygen, then it will be immediately able to calculate the correct difference to 100% as oxygen, and of course then also the other elements will sort out correctly. So I wanted to show you here these two ways. Either you define the elements as oxides to calculate the results, or you leave it open and you calculate them as element and you just say the rest is oxide, is oxygen, and then both ways will work. Here you are a bit more flexible in case your elements are not always in the highest oxidation state. Another example are press pellets. And when we do press pellets, normally we have to use a binder that we get a mechanically stable pellet, which then also can be measured in vacuum. And so what do? We mix our sample with binder. And for this, normally it's good to use a small mixer so that it's really homogeneous. Then we pour it into a pressing die. We press it, let me say, up to 25 tons. And then we take out our pellet and can measure it with the XRF instrument. And here we have then to define the parameters so that UniQuant can do an evaluation. And in this case, I use the material which is very complicated. So it's a black mass which comes from battery recycling, and it's a mixture of graphite and metal oxides. And if I want to analyze such a material with UniQuant, I have, of course, to describe the sample as good as possible. And the first information I put in is that I want to evaluate the elements as oxide. Then I know that these elements, carbon, hydrogen, oxygen, nitrogen, and lithium, I cannot measure with this instrument. So, but I have one information available. This is how much carbon is inside. So that means one unknown is then already taken. The second, the oxygen, is given by the stoichiometric. So there are still 3 elements left. Then I tell how height is my press pellet. And I use a copper list also, which was optimized before with a few black mass reference materials. I tell the software it's vacuum I use, and the background is adjusted fully automatic. I need to tell the dilution factor with the wax, which is 1/4. And here in this case, I normalize. Why? Because in a press pellet, we have particle size effects, and there's always a part of information missing. So very often you get only a sum of 80%. But of course, here I want to know everything. So in this case, I normalize, but this means that when I give carbon at 46.4%, the rest of the result is then normalized to 53.6, so just filling up to 100%. This is what I would get as result. So we have this known rest of carbon, we have our sum 100%, we have the dilution specified, and you see in such a black mass what we find always is fluorine. We have some light elements here like aluminium, silicon, and phosphorus, and then the important ones are manganese, cobalt, and nickel. So it's an NMC black mass coming from an NMC car battery. And this is what is good for us when such a sample comes into the laboratory, that we can identify what kind of black mass is it and in what range are the NMC metals, because there are big differences in the concentration ratios, and this job UniQuant can do very easily. Of course, I know that I didn't take the lithium into account, which is normally around 4%, but this is the compromise I have to do here because I can't measure lithium. Another example is when we do oil analysis, and we have an unknown oil we want to detect. Then normally what we do is we use a sample cup. We have to prepare with a film. So the film is included into 2 rings and stretched. Then we fill our oil inside, and finally we measure the sample cup with the oil and close it with a lid. So when I want to put this into the UniQuant software, I have to define that I want to measure the elements as element. Yeah? Then again, I have a matrix I can't measure. I have to define the film I'm using, in this case a 6 micrometer polypropylene. I define how much sample I really filled into it. And I again have a kappa list, which is based on the main factory calibration, but a little bit fine-tuned with a few oil standards so that it gives more accurate results. I measure under helium atmosphere, and here my background is taken from a blank oil sample, which was defined before. I have no dilution, and I let UniQuant really calculate the rest to 100% over my given matrix of CH2. So this is done then fully automatic. So if we look on the result, we see that UniQuant has detected that 98.5% is oil as the rest of matrix, and the rest are elements I can detect. And in this case, actually, I used a control sample as glass, which just simulates an oil, but gives me the good possibility to measure this as a control sample again and again without always using a new certified reference material. And this glass was designed to have most of the elements in the range of 500 ppm. And you see how good this comes out in such a measurement. Another example are polymers. So here I got 3D printed pellets from different polymers. They were all white, so they contain titanium dioxide as the color white. And we know the formulas, of course, of these polymers. And then what we did is we etched the materials and we used wet chemistry to get the titanium content. And then we measured the same pellets in UniQuant by defining really the exact matrix. And we get a very good agreement between the two analytical methods, because also in UniQuant it was exactly specified what is the matrix. If I just would tell UniQuant that I have CH2, just one polymer matrix, like in a polyethylene sample, you see we will get really a big difference in the results. And this is just to show you how important it is that your sample is described correctly when you want to measure with such a software. Last but not least, I have here an example from a 3D metal powder, which is often controlled when they buy these materials from third party. They want to know, is it really fitting to the specification? I can easily do that when I fill the sample in a sample cup. So I use a film as a bottom, I measure under helium, and I put just 1 millimeter of material inside. If I just would measure it with UniQuant, I would just get a sum of 84% because of all these holes inside and the particle size effects. I lose some information here. And this is the reason why we do not get 100%, so we get about 15% less. But then I use the trick to normalize it to 100%, and then I see that this material really fits nicely to a stainless steel specification. And so this is another example how you have to tell the software how you want to measure and how you want to evaluate. And then, of course, you get a good answer out of it. Okay, let me summarize my presentation of the applications for my laboratory. So first I presented you that we use it for glass to do the production control of drift monitoring. When we develop new fuse speed recipes, we check them by the standardless software if the reproducibility is correct. We can measure any liquids coming into the laboratory. We use it for press pellets just to verify what elements are present and what is the further strategy in analysis in the laboratory. We can use it for all kinds of polymers and, of course, loose powders just for a quick check of the qualitative analysis, we can say, of the elements present in the sample. So I can say it's really a universal tool to either just find out more of the samples or even do really quantitative analysis. Okay, and now Lynn will also give you a summary from their presentations.
Thank you. Thank you, Rainer. It was a very interesting presentation on the applications to show the accuracy of UniQuant. So from my part, just a summary of what we presented today. We started with some basic introduction of UniQuant, what is required as a hardware and what is the product that we're offering, and some basic how we do the peak-to-peak hopping and what materials we can analyze with UniQuant. And then we focus on some applications in different industries with UniQuant. We showed example with cement, with precious metal, with alloys. We also showed you the 3D mapping using UniQuant. And we also emphasize it's not just for WD application, it's also for ED, so on mill powder, and also from catalyst. Yeah, so that's what we have presented today. And thank you very much for your attention and for your participation. Now, I think we can move to the Q&A session.
Yeah, right. And there are two questions in the moment. I think the first question is about fine-tuning of copper lists. Perhaps Didier, you can say there something to that.
Yeah, so the fine-tuning, in order to do the fine-tuning, you first need to select what type of material you want to fine-tune the kappa list for. You need to have at least one standard corresponding to this matrix material. And then you're going to use that known standard sample with known concentrations in order to adjust the intrinsic sensitivity, because any sample kappa list that covers all the different applications with which you could do analysis of metals, of paper, of oils, it is an average of sensitivities for each line. And then we can, by the fine-tuning, we can decide to use the absolute value for a given matrix, the sensitivity that corresponds exactly to a given matrix, rather than having an average for several matrices. So that's really how is the fine-tuning done.
Okay, thank you, Didier. There's another comment that we should pay attention to significant numbers. Yes, of course, this is true. We know that XRF is starting with in the ppm range to measure. And if this figure is true, what you write here, then it would be an error. I apologize for that, but you are absolutely correct. There's another comment. Do you have glass beads for alternative fuels such as textiles, plastics? Yeah, we can really simulate any kind of sample in XRF. That means I can always design synthetically a sample where I put the elements inside, so that, for example, if you have basic in plastics, I can also have a glass bead with these elements out of elements which are volatile. I mean, mercury is an example which is impossible to put into a glass, but all the other, especially the metals, we can do. There's another question concerning OptiQuant. Does normalization have to be 100%? Perhaps, Didier, you have an answer to that?
Could you repeat the question?
Yeah, when analyzing using OptiQuant, does normalization have to be 100%? What if the normalization doesn't reach 100%?
Okay, yes. Yeah, okay. OptiQuant was the name we used for UniQuant when measured on an Optimix spectrometer. We have now stopped using that name, so we use UniQuant all the time for all the applications, all the spectrometers. And yes, the sum before normalization gives you some information. It gives you, first of all, maybe your sample is not pressed completely. If you reach above 90% on a pressed pellet, this is usually normal, because there are some voids, as Rainer has shown in his presentation. There are some voids in between the grains, and therefore the whole volume is not completely filled with material, and therefore we should get some before normalization that is slightly below 100%. Sometimes you may find some before normalization that is around 60%, for example. And this should tell you that, okay, I'm missing some elements. UniQuant did not measure all the possible elements. So probably there could be a loss on ignition that you have to take into account, or there is some carbon in the sample representing quite a big part of the sample, or maybe another non-analyzed element like boron, like nitrogen. So these are the possibilities. Another possibility is that the sample is smaller than the 29 millimeter diameter that you normally measure. So if your sample is not covering completely the aperture of your sample holder, then your normalization, your sum before normalization will be smaller than 100%. And sometimes you may find higher than 100% before normalization. And this might indicate that, in fact, you're not in presence of a metal, but it's a sulfide, for example, and you may have then more than 100%, and you have to then specify that your sample is a sulfide, and it will correct your final analysis.
Okay, thank you. There's another question for you. Have you tested your software for the quantification of trace and minor elements in vegetal materials, such as plant leaves?
Yes, this can be done too. The difficulty or the peculiarity is how can we present the sample to the spectrometer. Either some people grind the sample at freezing temperature so that the plant become brittle, and then you get like a powder and you can press it and you can analyze it. Otherwise, it's also possible to measure small bits, so cut the plants, measure small bits of sample, put them in the same type of liquid or plastic cell for liquid analysis, try to fill as much as possible to have a thick layer of plant, and then you can do the analysis in helium or even in vacuum if your plants are dry enough, and just close the lid to the little sample cup and do the analysis.
Okay, thank you.
Of course, you need to enter the mass. Of course, you need to enter the mass of sample. That's very important, and enter an information that there is a rest not analyzed that is probably cellulose that UniQuant can measure.
Okay, then here is a question to me, which device did you use for application you presented? So it's a Perform X with a 4 kilowatt tube. Then there's another question. Does the catalyst need to be updated when the X-ray tube or detector is changed? This is for you, Didier.
Oh, well, in fact, we supply what we call the setting up samples, so drift correction samples, and these can be measured from time to time, maybe every 15 days, in order to correct for any drift, and also to correct if you have changed of detector or X-ray tube.
Okay, then there's another question. If we get a copy of this presentation, yes, this presentation is put on a YouTube channel from us and from Thermo, so that you definitely can watch it later on. There's another comment. You should provide some video examples to show fine-tuning for UniQuant. Yeah, that is a good idea. But of course,
good suggestion.
Yeah,
Yeah,
you can also perhaps see one of our courses to get some deeper information. Yeah, that would be an alternative. Then, does FLUXANA provide a calibration set for clay and soil samples that can be contaminated with nuclear and radiological elements like uranium and thorium? So we can provide calibration sets, but not with uranium and thorium, because here we have a lot of restriction in handling this. So this might be difficult and has to be discussed more in detail. So you can just contact me offline for that. Here is, can you provide standards that simulate plant materials, for example, based on cellulose? Yeah, that we did very often. That means we use cellulose, and for example, we add heavy metals, and then we grind it, and then we make pellets out of it. That works. Yeah, that is not a problem. If the samples are in gel form, would it be appropriate to use a mylar film as a support, or is it restricted to solid samples only? Now, you could handle it like a liquid, I would say, and then measure it under helium. That might be a possibility. Did you measure Gale samples, did you?
Gale.
Yeah, Gale, that is like yeah,
I think we had some.
half liquid.
Okay, some sort of pastes.
Yeah.
Okay, the difficulty there is it could be inhomogeneous. And in that case, it's better to turn, because then you may have a part that is liquid and a part that is solid, and they could separate quickly. So there's a way to make this sample half solid, to turn it into a paste. For example, by mixing with a carbon powder, or by mixing with alumina. But of course, if you mix with alumina, then you will not be able to measure aluminum, because that will be part of the matrix. But you turn the sample into a paste, and then it's much more homogeneous. You don't have the liquid part that separates away from the solid part. And then you do analysis like a liquid in helium, and you get quite good results, yes.
There's another comment on all the examples we saw, only height was factored and never weight. So of course, this is my error. I didn't mention that I also put all the time the weight for my dilution material and for my sample into UniQuant. Otherwise, UniQuant cannot correctly calculate. So that is,
Yes.
the weight is necessary. That is a fact. There's another question. Is it possible add integrated UniQuant to existing Perform X, an old Perform X with 9 correction drift samples?
I think this really depends on what kind of system you're having, and so we have to have a look, because so in general, relatively difficult. We do the calibration in the factory, but contact our after sales, then we can have a look.
Because you need to have the correct crystals installed. A collimator, of course, in a Performix, they are already installed, and the primary beam filter as well. But you need to have the correct crystal.
Yes. The standard crystal does not cover the whole for UniQuant. So UniQuant is normally specially configured with 4 crystals.
Okay, there's another question, and this is concerning the zinc sodium overlap. And zinc oxide is up to 23%, and he's interested if a UniQuant can measure this. Of course, the physics are the same for all kind of software packages. So if there's an overlap and the line overlap correction, which is in UniQuant present, is not able to handle this, then it's just not possible. So I would say you have to try out to which concentration it works, and then it will work, but not more. I don't. Perhaps.
It's a big overlap.
Yeah.
But of course, you can. That's a typical example where you need a fine tuning, because you need to adjust really well your zinc overlap on sodium, because it can easily be too much correction or not enough correction, because you have a very high zinc presence.
Yeah. But at 23% zinc oxide, it's probably very difficult to.
It's not easy. No, it's not easy. Especially the sodium is probably quite low.
Yeah, that's it.
Then you get to the trouble that your statistics of counting of the zinc is larger than the sodium signal, and then you can't really do a measurement, a proper measurement.
There's another question of fine-tuning the copper list using a control sample. So, however, the modified catalyst is not able to measure other control samples. Yeah, if you use press pellets, it's of course that you then adapted your catalyst to exactly this kind of press pellet, and when you use then a different one, then it will not fit. So perhaps we can discuss this further offline, so that you send us your example, and we can see how you can perhaps get a catalyst for different control samples. I think this has to be checked in detail. What else? Can we buy CRM? You should send me that offline so I can look in the lists. What else we have? What power do you suggest is optimum for a 4 kilowatt system? 80% or always to maximum power? I mean,
Well,
yeah, that is for you,
typically,
Didier.
typically, if you have a car that can run to 180 kilometers an hour, you're generally not using it all the time at full speed. So it's a little bit the same thing here. Different if you have a 2500 watt system, a per4 mix with 2500 watt, then we use it at 2500 watt all the time because the X-ray tube is in fact a 4200 watt X-ray tube. So the tube is not used at full power when we work at 2500 watt. So then you are also saving on the tube lifetime.
Okay, that's the very last question. R5 crystals, and then you should have a look on that list. It's AX03, germanium, PET, LIF 200, LIF 220, enough for geological samples using Perform X 4200.
Yes.
I think yes, yeah.
Yes.
Yeah.
We have also a special package for GeoQuant calibration, which raises the power to 3.6 kilowatt. So that could also be a optimized feature for UniQuant.
Especially when you look for trace elements in geological material, it's a good alternative.
Mhm.
Yep.
Okay, I think that's it. We answered all questions, and I hope everybody is very happy now. And I would say thank you. It was very interesting also to see that you have sent us so many good questions. And I hope you enjoyed our webinar today, and we could show you some good examples of the daily work. And from my side, I would thank you, everybody, and say goodbye.
Yep.
Yeah.
Thank you
you
very
from
much.
our side. Thank you for your joining.
Bye-bye.
Have a nice day. Bye.
Have a good day. Bye-bye.
Bye-bye.